Welcome, and let me use the opportunity to wish you a happy new month today. All right, now today we are going to be discussing isomerism. All right, isomerism. It's talking about isomers. It is not a new thing, but it's something that is quite interesting. This is something that has much to do with organic chemistry. Now, I'm Dr. B, your science teacher online. All you need to do for me is to share this class, and then you also assist me in subscribing. The subscription to this very channel is free. So you go to YouTube and you type Dr. B Science Classes. It will come up. All you need to do is to tap on the subscription bell and take all. And you share this class with your colleagues and friends as well and ask them to subscribe. Remember to tell them that subscription is also very free. No one charges you. So that anytime we come up like this, it will pop on the screen and then they be part of what we are doing. Now, do not also forget that there's a Facebook part of this, and it is still Dr. B Science Classes. When you go there, all you need to do is to follow. And then when you follow, you can like, drop comments, and even their questions will attend to you. We also have this on TikTok, and it is still the same Dr. B Science Class on TikTok, and you are going to see a very wonderful work that is done there. Alright, so let us look at isomerism. But the question is, what is isomerism? We have been hearing of what isomers are. So today we are talking about isomerism. So isomerism is just a process that gives rise to isomers. Alright, yeah, so it's just a process. So isomerism can just be seen as a process. Now when we say isomers, we are basically talking about, just like when you talk about allotropes, okay, and isotopes. So we have also isomers. Do not forget that there are all these things are built up from a particular type of a compound, okay, that will exist in two different forms as the case may be. But there are one or two properties of these forms that exist that makes them quite different and are classified as either isomers or even allotropes or even as the case may be. Alright, so when we look at isomers, it is just very easy for us to say that they are just different groups of organic compounds. They can be two groups of organic compounds or three groups of organic compounds or even more than three groups of organic compounds that exist with the same. You have to take note of this now, what isomers are. These different groups of organic compounds exist with the same molecular formula, but they have a different molecular structure. Now, this is what defines what isomers are. So, isomers have same molecular formula, but they have different molecular structure. This is all that defines isomerism. Two or more organic compounds with the same molecular formula but different structural formula. That is just it. That is just it. So once you know that once you see two or more organic compounds with the same molecular formula but different structural formula, it means that they are isomers. They are isomers. They belong to one parent group. Alright, but something is differentiating them. That is what it means. And these isomers will take up certain chemical properties that are a little bit different. Okay, that distinguish them from each other. Alright, now, and they also have another type, they also have some chemical properties that also make them similar to their parent organic compound. Alright, now that we know that isomerism simply explains a situation where you have two or more different organic compounds with the same molecular formula but different structural formula or molecular structure, we now step down to understanding the different types of isomerism that we have. Because it's not just enough to know that isomerism is that, but we have different types of isomerisms defined by different type of parameters. Okay. Now, when you look at now back here, when you say same molecular formula, what do you mean? I hope you know that methane is CH what? CH4, right? I hope you also know that C2 S6 is what? Is ethane, right? Okay, these are their molecular formula. I'm sure you know that C2H5OH is ethanol. This is the molecular formula for ethanol. You can also draw the molecular structure. So while molecular formulas um, are just being written, okay, now the structural formula or the molecular structure are the diagrams that depict the molecular formula. So molecular structures are drawn out of molecular formulas. We are going to look at that. Now, if you look at isomerism, we have what we call structural isomerism and stereoisomerism. There are the two major types of isomerism there are. You have others too, but the two major isomers or two major isomerisms are structural isomerism and stereoisomerism. Now, what is the difference between the structural isomerism and the stereoisomerism? The difference is clear. Now, when you take a look at the structural isomerism, it's already letting you know that it has to do with differences in structure. It is more like the definition of what isomerism is. The difference is just small. Now let's look at the difference between the structural isomerism and isomerism as it is. We had said that isomerism as it is deals with, or describe rather, two or more different organic compounds that possess the same molecular formula but different structural formula. It is the same thing for structural isomerism, except that the structural formula is being defined on the basis of the arrangements of the carbon atoms in the chain. That is just it. Because in the structural isomerism, it deals with basically the arrangement of carbon atoms in the structure in the chain. Okay, that is just what defines structural isomerism. Make it quite a little bit different from its the parent isomerism definition. Okay, so why we are looking at the similarity in the molecular formula of the organic compounds, their structures are different, and their structures are defined basically by the arrangement of the carbon atoms. Now that brings us down to the type of structural isomerism. Now before we get here, how about stereoisomerism? Because we said we have structural isomerism and stereoisomerism. So if structural isomerism has much to do with the differences, or rather the similarity in the molecular formulas of these particular organic compounds and the difference in the structural formula, how about the stereoisomer? The stereoisomerism is simply telling us about the similarity also in the molecular formula, but there is a difference in the spatial arrangement, the spatial orientation of the various carbon atoms. All right, the spatial arrangement or the spatial orientation of the various carbon atoms or groups along the chains. All right, along the chains. So when you take a look at the stereoisomers, we are basically seeing a situation whereby you have two or more different organic compounds with the same molecular formula but different spatial arrangement of their groups along the various carbon atoms, or even ring structures, okay, or even carbon atoms that are arranged in the midst of about four different groups. Okay, so once there is a sort of spatial arrangement or orientation, we are describing such isomers under stereoisomerism. While here in structural isomerism does not really bother itself about spatial arrangement or orientation of atoms or group of atoms, stereo bothers itself. Once there is differences in the arrangement, in the spatial arrangement or spatial orientation of atoms or group of atoms, all right, along the carbon-carbon double bond or ring structures, or even carbon atoms that lie in between four different groups, we classify this kind of isomers under stereoisomerism. We are not talking about stereoisomerism today. In the next class, as you follow me, we are going to discuss intensively stereoisomerism. But just know that stereoisomerism discusses similarity of two or more different organic compounds. In their similarity in their molecular formulas, but differences in their spatial arrangement of atoms or group of atoms along carbon-carbon double bonds or ring structures. Okay, but we are going to be focusing, and let me put this off because we are not talking about stereoisomerism today. So let me put this off. We are going to talk about basically about structural isomerism, where there's differences in structure, in molecular structure of two or different organic compounds come to play. Now, we have what we call the chain structural isomerism. So it means that we have chain isomers. Yes, we have chain isomers. Okay, so once you have two or more group of organic compounds with the same molecular formula but different structural formula in line with the arrangement of the carbon atoms along the chain, it becomes a chain isomer. Okay? So once you have isomers such that they have the same molecular formula but different structural formula on the basis of the differences in the arrangement of their carbon atom along the chain, those isomers are grouped under chain isomers. Example, it's something like, for example, you have something like butane and 2-methylpropane. Now, if you take a look at butane, you know that butane is C4H10. As far as you have two or more different organic compounds that have C4H10, it means that they have the same molecular formula, but their structural formula are different in such a way that their carbon atoms are arranged along the chain in different ways. They are chain isomers. Now, let's take the structure. This butane is 1, 2, 3, and 4. Ordinary butane is written in this way. So this is hydrogen, 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 hydrogen. This is butane. It's an alkane. So it has C4H10, a saturated hydrocarbon. Alright, so this is butane. Now, if there is another compound, an organic compound, that have the arrangement of carbon atoms separately, different from this, but the same molecular formula, then it means that it is an isomer. In that case, both of them are chain isomers. For example, 2-methylpropane. Now let us look at 2-methylpropane. 2-methylpropane. It is also an alkane. Okay? So, you say 2-methylpropane. So, propane itself is C3. Okay? Now, it means we have 1, 2, and 3. But here is 2-methyl. So, this is 1, 2, 3. So, in 2-methyl, we have C in this form. So, I have H, 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 H. Alright? Okay. Now, if you count the carbon atoms, you'll see that we have 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8. Alright? So, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms, hydrogen. So, this compound is still C4, 1, 2, 3, 4. And H is 10. So, it's still like this compound here, which is butane. So, both of them have the same molecular formula, but different arrangement of the structures due to the arrangement of the carbon atoms. In that case, 2-methylpropane and butane are chain isomers. I'm sure you understand what I'm talking about here. So both of them are isomers, but they are chain isomers because they have the same molecular formula. Look at it, 1, 2, 3, 4, 1, 2, 3, 4. And then hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is C4H10. So both of them have the same molecular formula, but their structural formula is different. And the difference is because of what? The arrangement of the carbon atoms along the chain. This one is straight chain arrangement, and this one is a branch chain arrangement. Right? This is a branch chain hydrocarbon, 2-methylpropane. This is a straight chain hydrocarbon, butane. But both of them are isomers, and they are what? Chain isomers. Up today, you understand what chain isomers are, and a good example of a chain isomer. Now, let us look at this. The functional isomers. What are functional isomers? We already know that as far as they are isomers, they have the same molecular formula. But what makes it a functional isomer? It is because of the differences in their structure based on the position of their functional group. Yes. Or perhaps we should even say position of functional group. We should say just based on the presence, the differences in the functional group. Yeah. So it means that if you have two isomers or two or more organic compounds that possesses the same structure, the same molecular formula, but different structural formula as a result of the functional group they carry, we will term them as functional isomers. They are all structural isomerism. They are all under the process. Now let's just take a good take a look at a good example of this. You can look at something like ethanol and something like methoxymethane. Alright, so if you look at ethanol and methoxymethane, they have the same molecular formula, C2H5OH, but because of the differences in their functional group, it changes their structure. Hence, they become isomers. And those isomers are not chain isomers. Those isomers are functional isomers. Now let us take a look at an example. Let me clean this. Okay, so we are looking at ethanol. Ethanol is C2H5OH. And methoxymethane, okay? Methoxymethane is the same. Methoxymethane is the same. Now, look at the structure of ethanol. Ethanol is 1 and 2. And this is hydrogen, 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 hydrogen. And this is OH. This is the functional group. This is the functional group for ethanol. Alright? C2, 1, 2, 3, 4, 5. Alright? And an OH. Now let us look at methoxymethane. It is the same. Now we're going to have C. In methoxymethane, we are going to have C, O, and C. This is hydrogen, 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 hydrogen. And here is a functional group. Did you see? So you have 2 carbon atoms, 1, 2, 3, 4, 5, 6. This hydrogen attaches to this to make it OH. So you still have the same C2H5OH. And this is methoxymethane, and this one is ethanol. They have the same molecular formula, different structural formula, and the different structural formula is because of the difference in the functional group they have. In that case, both of them are what? Isomers. And these isomers are functional isomers. Are you getting what I'm talking about? Now, if you are glued to the screen, you will see that we are making sense here. Okay, we are trying to explain what chain isomerism, chain isomers are, functional isomers are. We have mentioned what chain isomers are already when we talk about isomers that are created or been established from two or more organic compounds that have the same molecular formula but different structural formula on the basis of the arrangement of carbon atoms along the chain isomers. We have mentioned butane and 2-methylpropane. We have other examples, but these are common examples. We have mentioned functional isomers, the same two or more different organic compounds with the same molecular formula, different structural formula on the basis of the type of functional group they possess. And we have mentioned ethanol and methoxymethyl. Now, how about position isomers? Position isomers. Both chain isomers, functional isomers, position isomers belong to structural isomerism. How about position isomers? Now, when you look at position isomers, it is quite closer to functional isomers. But in this case, we are talking about differences in the position of what? Of the functional group, and not the difference in the type of functional group. In the functional isomerism, we are looking at isomers that have different functional group, not because of their position, but they have different functional groups. Now, when you have two different isomers that have the same molecular formula, but they have the same functional group, but the position of their functional group differs, we now classify them as what? Position isomers, not functional isomers. You must take note of this. Position isomers, they have the same the same functional group, but the position of their functional group is different. That makes their structure also different. Position isomers. Now, example is something like but 1 in and but 2 in. But 1 in and but 2 in. Okay, so you have something like that is for this. You have something like but 1 in and you have something like but 2 in. These are alkene. They are not alkane. These are alkene, unsaturated hydrocarbons with double bonds. Okay, so these are typical example of isomers that are classified as position isomers. Let's take a look at but 1 in. Now it's from butane. Okay, butane. Right. So it's expected that we have double bond at the first carbon atom. Okay, so I have double bond at the first carbon. So we have 4. So we have 1, 2, 3, 4. Okay, so but here this 1, this 2, this 3, this 4. So but 1 in, it means there is a double bond here. Because this 1, this 2, this 3, this 4 carbon atoms. So but 1 in means we have a double bond at the first carbon atom. Now this will give you hydrogen, 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 okay, hydrogen, and hydrogen. Okay, so this is but 1 in. Now for the but 2 in, it means that we have 1, 2, 3, and 4. There is a double bond at the second carbon atom. That's why it's called but 2 in. Okay, so here we have this. Okay, and this is but 2 in because the functional group, which is the carbon-carbon double bond, are in different positions. The same functional group in different positions give the structure a different structure. Position isomer. So if you take a look at this, you see that this is CH2, okay, CH, all right, okay, and okay, CH3. All right, so CH3, CH2. Okay, so this is C2H2. Okay, so CH2, CH2, and this. Okay, so you have something quite closer to this, describing your butene. Okay, so you have a CH2 double bond, you have a CH, and then you have this. So you have a structure of this nature, and then here you also have your CH3, okay, and then here you have CH, okay, and then you have CH, you have CH3. Now if you count the number of hydrogen and number of carbon along with this, you see that you have the same carbon atoms, the same hydrogen, and then the difference is the position of the double bonds. In that case, it means that because of the differences in the position of the functional groups, here is 1, here is 2, okay, which makes the structure different, you now classify these isomers, but 1 in and 2 in, as position isomers. Alright, position isomers. So that is how you classify. That is how you classify. That is how you classify the structural isomerism. So structural isomerism on chain isomers, on functional isomers, on position isomers, we have this course. Okay, so today now, if you go out there and someone is asking you about about isomerism, about structural isomerism, you should be able to explain to the person what structural isomerism is all about. All right, so here you have, okay, we didn't put down this. So here you have CH3, CH double bond, CH3. Okay, so that is it. So you see CH3 here, and then you see CH, you see CH, you see CH3. Okay. So that is how it works out. So here as well you have a double bond here. So here you expect to have CH3, CH2. Okay, so this is CH. There's CH here, there is CH2 here. Alright, so okay, alright, sorry. So you have CH, you have CH2, you have CH, you have CH2 and CH3. Alright, so here you have both 1 in and both 2 in. The difference is only because of the position of their functional group, which changes the structure of the compound, but the molecular formulas are the same. So it's been pretty nice having this class with you today, discussing what isomerism is, what structural isomerism is, and what the types are, from the position isomers to the functional isomers down to even the chain isomers, with possible examples and explanations of structures that define or explain this explicitly. Now, the next time we're going to have our class, we are going to look at stereoisomers. Stereoisomerism. We'll look at the types of stereoisomerism, why we classify stereoisomers as group of organic compounds that possess same molecular formula and a different spatial orientation of atoms or group of atoms along carbon-carbon double bond, or along range structures, or even along carbon in the presence of 4 different groups. Now, do not forget that you need to share this class with your friends. Don't forget to tell them to subscribe. What is coming ahead is something big and very interesting, and you do not need to miss as well. So once they subscribe, leave comments in any form of questions or appreciation, and likes as well.